Hello everyone. This presentation is about directly cooled windings in switched reluctance machines. The paper ID of this presentation is 001899. This work was done before in a hypercool project together between Ghent University and Flanders Make. Flanders Make is the strategic research center for manufacturing industry in Flanders. My name is Mohammed Ibrahim. I am a postdoctoral researcher at Ghent University and Flanders Make at UGent, Department of Electromechanical Systems and Metal Engineering. My research areas include design and control of electric machines and drives for industrial and sustainable energy applications. And this is my email for further contact. The outlines of these presentations are: first, I will give introduction. Second, I will show the stator setup, and then electromagnetic analysis and experimental validation and thermal analysis, and later I will give some conclusions. Let us start with introduction. It's well known for everyone that there is a great demand to increase the power density of electric machines, keeping a limited size, such as, for example, in electric vehicle. To do so, there are several possible ways. One of them is to increase the current density inside the machine windings. However, this increases the losses and accordingly the temperature of the machines. Therefore, cooling system is necessary. There are several cooling techniques for electric machines. They can be classified into direct and indirect methods to extract the heat from the system. Some examples of cooling methods are forced air cooling, water jacket cooling in the housing, direct coil, or slot cooling. The topic of this presentation is about direct cooling techniques or slot cooling technique. In the stator of electric machines with concentrated windings, with non-overlapping windings, it is possible. You can see here between the windings, there is a free space. In this space, it is possible to insert a cooling tube to cool the windings. Looking into the literature, most of the work done on the direct coil cooling has studied the thermal influence of electric machines. However, electromagnetic influence of direct coil cooling on the performance of electric machines has not received a considerable attention in the literature. Therefore, the main research question of this presentation is: what is the influence of inserting cooling tubes between the windings of electric machine on the losses and hence the resulting temperature distribution? To answer this question, we did the following analysis. Next point is stator setup. We have simplified the analysis to consider only a stator of electric machine with concentrated windings without a rotor. Therefore, it's called the stator setup. This stator can be a stator of switched reluctance machine or a synchronous machine or whatever. So it's a 6-pole stator with non-overlapping concentrated windings. And in this table, you can see most of the relevant parameters. Third point, electromagnetic analysis. We have simulated the stator setup using finite 2D analysis using Maxwell ANSYS. The 6 coils on the stator bolts have been connected in series, as you can see. A sinusoidal supply is used to inject a sinusoidal current in these windings. Based on this wiring connection, the flux distribution inside the stator setup is like this, or inside the stator core. We have examined 2 main cases. The first cases, we studied the influence of the conductivity of the cooling tube on the losses of the stator setup. Therefore, one material with low conductivity, which is stainless steel, and one material with high conductivity, which is copper, was considered. And the tube thickness itself was fixed at 1 millimeter. For your information, the conductivity of copper is about 58 megasimol per meter, while the conductivity of the stainless steel is about 1.35 megasimol per meter. So there is difference in ratio of about 43 times. We have computed the core losses of the stator core at different frequency of the supply and also different current amplitudes. As you can see, the core losses increases with the current and the frequency as known. But there is no influence on the core losses if we used a cooling tube in the stator or no. So there is no influence on the core losses. The main reason is that the simulation is done up to 1000 hertz, where the limited resistance effect of the cooling tube was observed. But probably at higher frequencies, there will be some influence on the core losses. For your information, we also examined this up to 2500 hertz, and we found that there is no influence on the core losses. For the copper losses, as you can see, also for different frequencies and the currents, neglecting the temperature and skin effect, we found that there is no influence on the core losses if we used a cooling tube or no. The main reason, as you can see here, is if you look to the flux distribution, this is the flux lines. There is some flux goes through the space between the coils. This flux induces eddy currents inside the cooling tube, but they don't influence the flux lines in the core. If we look to the tube losses, in case of stainless steel cooling tube, you can see that of course, when the current increases, the losses of the tubes increases, and also it increases with the frequency. The maximum cooling tube losses at the peak current, which is 40 amp. This 40 amp is about 14 ampere per millimeter square. And you can see here, it's about 4.5 watt. If we look to, in case of a copper cooling tube, you see that also the same trend can be observed. However, the value of the tube losses are much higher. Comparing the two figures, the one at stainless steel and copper, for low frequency, let's say 50 hertz, the difference between the losses between stainless steel and copper is about 43 times. This means that the copper losses is the tube losses in case of a copper tube is higher than the stainless steel by about 43 times at lower frequency, but at higher frequency, let's say at 1000 hertz, it's a bit lower, 27 times. This is because of a linear variation at low frequency with the conductivity. This 43 times is the ratio of the conductivity between the copper and stainless steel. And at higher frequency, there is non-linear variation due to skin effect. The second case, we studied a variable cooling tube wall thickness. So we changes the wall thickness of the cooling tube from 0.2 millimeter to 1.2 millimeter. For the two materials also, where we have stainless steel, you can see the core losses didn't also influence it if the thickness of the tube is changing. And also in case of the copper tube, also the core losses didn't change. If we look to the tube losses, you can see that with increasing the tube thickness, the losses increases. So the low thickness tube has the low loss, while the higher thickness tube has the high loss. And the times between them is approximately in a linear way between the times of the thickness. So you see here, it's a 4.5 times when you increase the thickness from 0.2 millimeter to 1.2 millimeter. And here, if you look in case of a copper tube, you can see the same trend, but the value is a bit lower. In this case, at about 14 ampere per millimeter square. In order to validate the simulation work, we constructed an experimental setup. As you can see, this is a controlled pure sinusoidal supply, and this is a power analyzer to measure the power. This is the stator, and you can see here the stator setup. In case of a stainless steel, we did the measurements in case of stainless steel cooling tube. You can see here, this is for different frequencies, 50 Hertz, 1000 Hertz, and 200 Hertz, and 500 Hertz. You can see that with and without cooling tubes, the losses of the cooling tube the losses are neglected. This is in case of stainless steel. This was observed also in the simulation. The next point is the thermal validation. From the electromagnetic analysis presented before, it's evident that a low electrical conductive material and much thinner wall thickness for the cooling tube is preferred in order to diminish the losses of the cooling tube. However, it is also necessary to further check if those are valid from a thermal point of view. Therefore, we will do some thermal validation. There are several parameters. A nomic cylinder of 0.1 millimeter between the coil and the stator, and the coil and the tube is taken into account. Also, a contact resistance of 600 millimeter Kelvin per watt is implemented. And also 50 per 50 mix of water glycol at 40 degrees with 10 liter per minute flow rate. And also we have connected the cooling tubes into parallel circuits. In each circuit, there are 3 cooling tubes are connected in series. As you can see here, this is parameters for the thermal model that we use at 40 amp current and 1000 hertz frequency. We have calculated before the losses of the cooling tube and the copper losses, tubular losses in case of 1 millimeter thickness of the cooling tube and 0.2 millimeter thickness. And this is in case of stainless steel and copper. We have used this parameter in the thermal model. As you can see here, this is the temperature distribution in case of stainless steel and 1 millimeter tube thickness. And this is also the temperature distribution in case of a copper tube with 1 millimeter thickness for the tube. And also at 0.2 millimeter thickness. The conclusion from these figures, as you can see, is that the temperature distribution is approximately similar using copper or stainless steel tube for both tube thicknesses. However, the maximum temperature of the stator setup components, you can see here the maximum coil temperature in case of stainless steel at large thickness, 1 millimeter and 0.2 millimeter is approximately similar. And also the maximum temperature in the stator itself is approximately similar. However, if you look when the cooling tube material is copper, you see there is about 2.5 degree in the maximum temperature of the coil and about 3.1 degree difference in case of maximum stator temperature between the copper and the stainless steel. However, here in the copper itself, when the thickness of the tube is different, you see there is also a little different in the temperature distribution. The conclusions from this analysis. First, the influence of inserting cooling tubes on the losses and the temperature distribution of stator setup is presented. Much thinner thickness for the cooling tube is recommended in order to diminish the tube ohmic losses, particularly at high frequencies. A compromise between a low electrical and high thermal conductivities for tube material is preferred. This is because the low electrical conductive material of the tube results in low ohmic losses, and the high thermal conductive tube material results in better convection. Eventually, the low ohmic losses of a low electrical conductive material of the cooling tube will be compensated by a higher copper losses because of a higher temperature. Thanks for your attention, and for a further question, you can contact me by email. Thank you very much.